I'd like to talk today about some algorithms that work very well for data mining. And unlike existing algorithms, these are based on combinatorial optimization and also network flow techniques. And typically, people were not using things like that in data mining because of concerns about computability and concerns about computation running times. I'm also going to talk about closely related topic that I call sparse computation. And this appears to be very useful for large-scale data mining. Here is an intuitive clustering criterion. So to find a cluster that combines two objectives. One objective would have a great deal of similarity between the objects that fall in the cluster. And on the other hand, it will have very little similarity between the cluster itself and its complement. So this combination of two objectives can be written either as a ratio, minimizing, and the expression there is the numerator, CS bar, indicates the total sum of similarity between the selected set S, which is required to be non-empty and not equal to the universal set. So this is the CSS bar is the total similarity between the set and its complement, divided by CSS, which is total similarity between the elements in the set S and themselves. Now, a linearization version could take a weighted linear combination of these two objectives. So this would be minimize the so-called cut, the similarity between the set and the complement, minus some lambda total similarity within, because the second objective is something we want to maximize, and the first one, the cut objective, we want to minimize. Another version is there is actually no reason why the similarity weights in the cut part, the in-between part, should be the same type of similarity weights as the within the cluster. So the indices of 1 and 2 allow for different types of similarities that will be derived. Now, I call this problem normalized cut prime because it is somewhat related to the known problem of normalized cut that has been used quite extensively, especially in image segmentation. And here are some related problems. So one related problem is the graph expander problem. So the graph expander problem can be written as, again, combination of two objectives that are expressed in the ratio. So minimize, find a set S. And here the set S has to be less than or equal to half of the total number of nodes in the graph. So find such set that will minimize the cut, divided by, or normalized, that's where the word normalized coming from, normalized by the size of the set. So this makes it, dividing by the size of S makes it unattractive to select small sets. And there is a bound that does not allow us more than half the total. This can be also written as minimize the cut divided by the minimum between the size of S and the size of the complement of S. Another related problem, the trigger problem, is a weighted generalization of the expander problem. And here we are looking for a set S. So with the value ds, now I have to say what ds is. With each node, we associate the weighted degree, which is the sum of the weights of the edges adjacent to the node in the underlying graph. And d of s is the sum of weights of or the sum of the weighted degrees of all the nodes in S. So we want d of S to be no more than half of the total sum of the weighted degrees. Just notice that if we just add the weights in the graph, this will be equal to half of dv, because each node, each endpoint count for an edge its weight. So if we sum on everything, each weight is actually counted twice. So, and this appears also as the Chigger constant, that is, as the minimize the cut divided by the minimum between ds and ds bar. So these are obviously equivalent. Now, this can be generalized. This is related to what I said earlier about the different type of similarity weights for the numerator and the denominator. We can give any weights to the nodes, and then look at an objective of a cut divided by Q of S, where Q of S is the sum of Qi, where Qi is the weight of node I. And that again can be written in this form. So obviously the Chigger constant is a special case of this. Now, the source of the naming of normalized cut is that Shi and Malik introduced this under this name, normalized cut. And the idea is that in image segmentation, cut is a pretty good approach, except that it tends to have in general either very single pixel or everything. So it does not differentiate very well the size, does not balance very well the size of the cluster. So the idea was to write it in this form. And they wrote it as cut divided by ds plus the cut divided by ds complement, which is equivalent within a factor of 2 to Chigger constant. It's an NP-hard problem. In a Nature paper in 2007, Sharon et al. Presented this problem as normalized cut, this one, and presented a way of solving it with the spectral method. And the question whether this is indeed equal to the normalized cut problem. So a little bit about this. How do these two problems compare? So here is the problem of Shi and Malik. And if you take the objective function that Sharon et al. Used, so this is the cut divided by the sum of similarities within, and then you can do some very trivial algebraic manipulation. So the cut divided by half ds minus the sum of, minus the cut. And then you divide numerator and denominator by a cut, and you get this expression. So minimizing this expression is the same as maximizing the denominator of it, which is what's here, which is the same as minimizing the reciprocal. So what you get is that the objective function that they proposed is actually not equal to normalized cut, but to the first term of normalized cut. And the normalized cut and this other version that I call normalized cut prime, both of them are invariably solved by the spectral method. There is a great deal of research how the spectral method works for that, and some other image segmentation problems. And the main applications are in image segmentation. This is just a quick, I don't think I want to spend time on this, how it's solved with the spectral method. Here the L is the Laplacian matrix. But actually, although the normalized cut is NP-hard, normalized cut prime is solvable in strongly polynomial time with a minimum cut algorithm. And it has an advantage of being able to, use different type of weights in numerator and denominator, and it gives a whole array of so-called breakpoints. That is all the possible trade-offs between the two objectives, the one in the numerator and the one in the denominator, all of this in the running time of a single minimum cut. And here is some relationship between how this relates to, I'm not giving you details about the algorithms, but how it relates to the solution with the spectral method. So here is a lemma which says that this expression of normalized cut, where the denominator can have weights that are different from the weighted degrees, can be anything, is equal to the following Rayleigh ratio. And this Rayleigh ratio has Y transpose, the Laplacian matrix, D minus W, Y, divided by Y transpose QY, where Q is a diagonal matrix that the entry on the ith position is Q of I. And then we have two types of constraints in this. First of all is what I call the orthogonality constraint, Y transpose Q times the vector of 1s equal to 0. And the other one is yi equal to minus b or 1. And notice that b is a quantity that is not mentioned anywhere here. But if you look, for instance, the special case where Q is the identity matrix, for instance, then, so all the weights are 1, like in the expander problem, then you plug minus b or 1 in the orthogonality constraint, so you have the sum of the y's is equal to 0. And that means that in one set, you can interpret if it's minus b, it's in the set S, and if it's 1, it's in the complement. It means that there is the balance of the number of nodes between the set S and the complement. This ratio is equal to b. So this constraint actually controls the balance. And in fact, this constraint is what makes the problem hard, not the other one. So indeed, the spectral relaxation, that is, it ignores these constraints, the binary constraint, the discrete constraints. And the remaining problem is to find essentially the Fiedler eigenvalue, because one corresponds to the trivial eigenvalue, which is 0, the smallest, and the second one, the second smallest, is the Fiedler eigenvalue. So this is what's done with the spectral method. With the combinatorial optimization technique, the idea is to relax this one constraint, the orthogonality constraint, and now the remaining problem subject to this requirement is actually solved in polynomial time. And as I said, not only you get an optimal solution for that, you get as a byproduct all the possible breakpoints. And you might say that there are too many of them. The answer is no. You can present all the possible breakpoints in strongly polynomial time and very compactly, actually in linear time. This is more on the spectral method, and I think I'll skip it. This is showing experiments done comparing the spectral method that was proposed in the paper of Shi and Malik. So this is one type of relaxation versus this, what I call NC prime, that is relaxing the orthogonality constraint. And in these pictures on the left, this is the original image. In black on the middle and the right, this is the segmentation of one set, and the rest is the complement. So the eigenvector result gives you this segmentation, and the combinatorial algorithm gives you this segmentation. So they look pretty similar, but if you evaluate the objective function of the problem that they try to model, that is this normalized cut, the objective function you get is 35 times 10 to the power 4, minus 4 with the eigenvector technique. And when you use the cut technique, you get 1.702 times 10 to the minus 4, so about a factor of 20 better. And this image is actually in the website of Xi, where he gives the code. He has a code for the spectral method for normalized cut. And this is another comparison with another image. So on the left, it's the original image. In the middle, this is what the spectral method gave. And as you notice, it cuts the sky in half, which is very typical because it gets the balancing right, but not necessarily the clustering. So this happens actually relatively often. And on the right is what you get with the cut technique. So if you plug it into the objective of normalized cut, you get here 127 times 10 to the minus 4, and here you get 1.4 times 10 to the minus 4, which is roughly a factor of 80 better. And this was a collection of runs done with Cheng Lu and Eric Bertelli. And in this collection, we compare the objective function of the spectral method to that of the combinatorial method. And the longer the bar goes to the right, the better on a logarithmic scale is the solution for the combinatorial. Better means lower because we are trying to minimize an objective. So on image 13, we had 20 images taken from the Berkeley benchmark of images. Image 13, it did better for one type of weight selection. For the other type of weight selection that is based, these are the lighter bar, this is based on entropy. The other one did always better and an awful lot better, even as much as 10 to the power 13 better. Now, so because of that, the thinking was that this is working pretty well in image segmentation. Image segmentation is a special case of data mining, obviously of clustering classification. Let's try to apply it to instances of data mining. I'm skipping because I don't have too much time. So this is one type of runs in which we were ranking drugs according to their effectiveness. And the effectiveness of drugs in this case was evaluated by looking at electron microscope images of the cells. It's called high content screening. And here, I don't have time to give you the setup of the experiment. It's only that in this graph, you have the training sample fraction is growing as we go to the right. And on the vertical axis, we have the accuracy, the mean accuracy, because each one was run on 1,000 trials. And the blue line on the top that gives the highest accuracy corresponds to this normalized cut prime technique, that is to the combinatorial algorithm. And we adapted for this also a support vector machine that is the green line, which is not consistently, but almost always second best. And other algorithms were ones that were used in the literature on this type of drug ranking problem, and they did a lot worse. Then we looked at taking just data sets without any knowledge of the nature of the data set. So these are small data sets from the UC Irvine Machine Learning Repository. And in all of them, we took binary class labels, and we looked at these 10 data sets. So there is the information about these data sets. Now, we were running them with this algorithm that I told you about, this normalized cut prime, that in this case we call it supervised normalized cut, so SNC. The other columns on the left, it's the neural network. All of them we did some tuning of parameters. So for instance, for neural network, we did tuning in terms of the number of hidden layers. Support vector machine, we did different kernels, and we polynomial kernel different degrees. Again, the experiment is described in a paper. And then linear regression, logistic regression, lasso, cart, k-nearest neighbor, and ensemble. And these are the results, the accuracy, the relative accuracy that we got. That is, one that gets 100% is the best accuracy. And SNC did very, very well, and SVM did kind of very close. And KNN in this experiment did not do that great, although later in other experiments we did get much better performance with KNN. So these are the relative accuracy. We took the averages. So in this one, is the normalized cut, and then ensemble and support vector machine are quite high up. And the regression-based models, all of them perform quite badly. That is, sometimes they get good results, but they are very unrobust. Then we try to expand it to large-scale data mining. But in large-scale data sets, the problem is that this model looked at similarity weights. Now, in images, we can look at similarity between each pixel and its neighbors. The neighbors are kind of physical neighbors in the plane, or in video, it's also similar in time. So basically, the number of neighbors or the degree of the nodes is pretty small. Constant, essentially. But when we have a data set, we don't know anything about the data set, then we have to compare each one to everything. So basically, we have a click. Now, when we have a large data set, the size of this matrix explodes quadratically in the size of the data set. So if we have a data set on 1 million objects, we cannot even think about writing the similarity matrices. Now, there are many approaches that would use sparsиfication. And I wanted to point out that sparsиfication is not applicable. Sparsиfication means that you look at the matrix, and usually you take an algorithm that, with a threshold or other technique, certain entries round them down to 0. But we don't have the space or time to even look at them and decide whether to round them to 0. We don't want even to look at them in the first place. So this idea of sparse computation is don't even evaluate entries of the matrix unless you need them, unless you know in advance that they are relevant. And in order to do that, one idea was, and this is reported in a paper with Philip Bauman. So one idea is to use so-called approximate principal component analysis. So we based it on the constant time SVD of the Rinius, Cannon, and Mahoney. And then we subdivided the range of the values in each dimension. So basically, we did dimension reduction. And in each dimension, we partition into buckets, and then assign each object to the bucket or the block based on its P entries. Now, the implementation of that is extremely fast. First of all, this sampling that is done to get this approximate PCA is very fast, but then essentially what we do is identifying the right bucket is equivalent to rounding to the first few significant digits. So this is a trivial operation. And then we compute only those that belong either to the same block or to so-called adjacent blocks. So adjacent blocks or buckets in this picture correspond to neighborhood that is similar to neighborhood that you get in image segmentation. That is physically in this generated reduced dimension Euclidean space, we find the distances. Let me show you, I'll skip that. So this we ran on large data sets. So the sizes of these data sets vary. The smallest is 2,000 objects, then we have 20,000, 45,000, and the last one is more than 500,000. And these are also known data sets. I'll skip this. This is the experiment design, which did 20% for tuning, and then for testing, 80% in which we split it into training and validation. So the numerical results are here really tiny, but what's relevant is that we partition each dimension to the same number of blocks. So as the number of blocks grow, the density of the function goes down. Maybe you really can't see anything, so let me show you these graphs. So these are numerical results. So first look at the left. So at the left, there are these 20,000 some data sets. And in these data sets, you have on the graph, you have the blue line indicates the density as the grid resolution becomes finer and finer. So the density diminishes, and the running time is actually linear in the density. So it is also diminishing. And the green line is the accuracy. And the accuracy is on the axis of the right side, and it barely changes within interval of 1%. The changes throughout, even you get immense reduction in density, the accuracy changes less than 1%. Sometimes it's even improving. The orange line is the density of the complete matrix. For the ones on the right, we couldn't do the complete matrix, so we started it with something less than the complete matrix. But the experience is similar. We get virtually no change in the accuracy and dramatic change in the density and therefore running time. The one data set, which is CO2, that has 580,000 objects, we got accuracy of 89.72, and even with density of 0.008. So we could compare to density that was derived from 100 buckets in each direction. But as you see, the density goes down dramatically. Accuracy barely changes. Now, we also tested, but that's very recently, for k-nearest neighbor, and the results are very, very good. K-nearest neighbors get very, very good accuracy. Now, in this table here, you can see the running time of sample values of k, number of intervals. So for 150, we get 5.2 seconds. For 500, we get 0.21 seconds, but still the accuracy barely changes. So the plan right now is actually, Alex Andoni, the previous presenter, suggested to use LSH, and we are starting to implement LSH as an alternative approach to approximate PCA and see whether this is changing in terms of accuracy and in terms of running time. So thank you.